Welcome back to Spectre AI. This is Spectre P. In today's video, we're covering the final step that actually makes quantum key distribution secure: privacy amplification. You're about to see why the raw key that comes out of QKD is not secure, why Eve still has partial information even after error correction, and how we use carefully designed hash functions to compress that imperfect key into something that's indistinguishable from true randomness. We'll look at the real math behind privacy amplification, walk through a simple example you can follow, and then break down a real-world failure mode where labs underestimate Eve's information and end up generating a key that isn't fully secure. So let's get started and see how privacy amplification turns a noisy, partially leaked raw key into a final key that even an unlimited adversary can't break. Let's start by looking at what the raw key actually looks like right after a QKD session. This heat map shows the distribution of bit values before any security processing. And as you can see, it's not uniform. There are visible clusters and patches of structure. And that's a problem. These patterns reflect statistical bias in the key. They come from basis announcements, detector imperfections, channel noise, and even side channel effects that an eavesdropper like Eve can partially exploit. So even after error correction, the raw key still contains correlations that make some bits more predictable than others. This is why privacy amplification is necessary. We need to remove these correlations and push the key toward full entropy before we can call it secure. Now that we've seen what the raw key looks like, let's walk through the step that actually transforms it into something secure: privacy amplification. On the left, we have the raw key. And as we saw earlier, it still contains structure, bias, and statistical patterns that Eve can partially predict. In other words, it's not ready to be used as a cryptographic key. Privacy amplification takes this imperfect key and pushes it through a universal hash function, shown here in the center box. This isn't a classical hash like SHA-256. In quantum cryptography, we use specially constructed hash families that guarantee information-theoretic security, even if Eve has quantum side information. What the hash function does is compress the raw key into a shorter output. And that compression is not a disadvantage, it's the entire point. By shrinking the key, we remove the correlations that Eve relies on and drive the entropy per bit much higher. On the right, you can see the compressed key. Notice that it looks more uniform, less structured, and much harder to predict. Eve's information has been reduced dramatically, and the security of the final key now depends on the entropy of the raw key, not its original length. This is the essence of privacy amplification. Eliminate Eve's knowledge by mathematically distilling randomness into its most secure form. In privacy amplification, we want to understand three things. First, how predictable the raw key is from Eve's point of view. Second, how close the final key will be to perfect randomness. And third, how many secure bits we're actually allowed to keep after compression. The first expression tells us how hard it is for Eve to guess the raw key in a single attempt. It measures her best possible chance of being correct, given everything she has learned from eavesdropping and side channels. When this value is small, it means Eve has very little certainty, and the conditional minimum entropy is high. High minimum entropy is exactly what we want, because it means the raw key still contains a large amount of genuine unpredictability. The second expression describes how close the final key will be to an ideal random key. This is where the security parameter comes in. It quantifies how different the final privacy amplified key could be from perfect randomness. Smaller values of the security parameter mean stronger guarantees for Alice and Bob because Eve's ability to distinguish the final key from a uniform one becomes extremely small. The third expression tells us how many bits we are actually allowed to keep after we compress the raw key using a universal hash function. The output key must always be shorter than the raw key, because the compression removes statistical patterns and eliminates information Eve could exploit. The amount of compression is determined directly by the minimum entropy and the security level we choose. If we require stronger security, we must compress more aggressively, and the final key becomes shorter, but also dramatically more secure. Together, these three relationships define the entire logic of privacy amplification. They tell us how unpredictable the raw key is, how secure we can make the final key, and exactly how many bits we're permitted to keep, while guaranteeing that Eve's information becomes mathematically negligible. In this example, we will take the abstract relationships from the previous slide and apply real numbers to see how many secure bits we can actually keep after privacy amplification. We begin with three inputs. First, the raw key contains 1,000 bits. Second, the conditional min entropy is 800 bits. This value comes from the parameter estimation step of the protocol and represents how much uncertainty remains from Eve's point of view after accounting for channel noise, detector imperfections, and any information leaked during error correction. And third, we choose a target security level of epsilon equal to 2 raised to the negative 40th power. This means we want the final key to be indistinguishable from perfect randomness, except with a probability of about 1 in a trillion. Using these values, we can now determine how much of the raw key can be safely retained. In the first step, we plug the entropy and the target security into the key length bound to compute the maximum number of bits we are allowed to keep. This gives a final key length of 720 bits. In other words, to reach our desired level of security, we must compress the raw key from 1,000 bits down to 720. That compression removes statistical patterns that Eve could exploit and forces the remaining bits to behave much more like a uniform random sequence. In the second step, we take the same numbers and evaluate how close the final key is to perfect randomness. When we plug the 720-bit output into the security expression, we find that the actual distinguishing advantage is bounded by epsilon equal to 2 raised to the negative 41st power. This is even smaller than the 2 raised to the negative 40th power that we initially required. So our final key is not just secure enough, it is slightly stronger than the threshold we imposed. Putting everything together, we started with a 1,000-bit raw key, compressed it to 720 bits, and obtained a final security level that exceeds our target. This demonstrates how privacy amplification converts a partially predictable key into a strongly secure one by mathematically eliminating Eve's residual information. In order to understand where the 800 bits of conditional minimum entropy come from, we walk through the same steps that a real quantum key distribution system performs whenever it estimates Eve's remaining information. We begin with a raw key that contains 1,000 bits. This is simply the number of bits that Alice and Bob share before any security processing takes place. The first step is to calculate how much of that key can be considered usable randomness after accounting for Eve's potential knowledge from the quantum channel itself. The channel introduces errors, and these errors tell us how much information Eve might have gained from her interactions with the quantum states. When we plug in a quantum bit error rate of 4% into the entropy function, we find that approximately 859 bits of genuine unpredictability remain from Eve's point of view. This value is called H1, and it represents the entropy that survives the quantum part of the protocol. In the second step, we compute how much information is lost during classical error correction. During error correction, Alice and Bob publicly exchange parity information that helps them reconcile their bit strings. Although the channel is authenticated, it is not encrypted, so Eve hears all of these parity messages. The total amount of information leaked this way is proportional to the binary entropy of the quantum bit error rate. If we choose a quantum bit error rate of 0.43%, The binary entropy is approximately 0.04. Multiplying this by the 1000-bit block size shows that Eve learns about 40 bits from the error correction process. These 40 bits must be subtracted from the previous entropy estimate. The third step is simply that subtraction. We take the 859 bits from the channel estimation step, subtract the 40 bits leaked during error correction, and obtain 819 bits. This is the amount of uncertainty that remains before accounting for statistical fluctuations. The fourth and final step is to apply a safety margin, sometimes called a finite-size penalty. Real systems never operate with infinitely many signals, so the observed error rates and statistics are subject to small fluctuations. To ensure that the security analysis remains valid even in the worst case, we subtract an additional safety term. In this example, we subtract 19 bits. This yields a final conditional minimum entropy of 800 bits. This value means that even though the raw key contains 1,000 bits, there are at least 800 bits of true unpredictability remaining once we account for Eve's knowledge from both the quantum channel and the public classical communication. This is the number that privacy amplification uses to determine how many secure bits can ultimately be kept. Privacy amplification is mathematically sound, but in real systems it can fail if the assumptions that feed into it are incorrect. The most common failure point occurs when the system underestimates how much information Eve has gained. If the parameter estimation step is too optimistic, the minimum entropy bound becomes too high. As a result, the hash function compresses the key less than it should, and the final key remains partially predictable. Privacy amplification also fails when the wrong type of hash function is used. Classical cryptographic hashes such as SHA-256 do not satisfy the universality requirements that the security proof depends on. When those requirements are violated, the leftover hash lemma no longer applies, and the final key has no information-theoretic security guarantee. A third problem arises from poor accounting of the information leaked during error correction. If the protocol reports fewer leaked bits than were actually revealed on the public channel, the system will again overestimate the remaining entropy. That leads to a final key that is longer than it should be and therefore insecure. Another source of vulnerability is the failure to apply finite-size corrections. Real devices operate with limited data, not with infinitely many signals. Skipping the statistical penalty term produces an inflated entropy estimate and allows Eve more information than the theory assumes. Finally, privacy amplification can fail because of incorrect implementation of the hash function itself. If the Toeplitz matrix is misaligned, if the seed is reused, or if there are coding bugs that create correlations in the output, the resulting key is not uniform and can be partially predictable. All of these mistakes feed into the same chain of consequences. A wrong key estimate leads to a wrong entropy estimate. A wrong entropy estimate leads to incorrect privacy amplification. Incorrect privacy amplification results in a final key that is not secure, even though the system may believe that it is. In this example, we look at how privacy amplification can fail even when all of the mathematics is correct on paper. The failure occurs because the system relies on assumptions about Eve's knowledge, and if those assumptions are wrong, the entire process becomes insecure. In this scenario, Eve performs a very subtle timing manipulation on the detectors. The effect is small enough that one detector fires slightly more often than the other, but not large enough to change the measured quantum bit error rate in any noticeable way. All of the standard statistical checks pass, and the QBER appears perfectly normal. Because the QBER looks clean, Alice and Bob assume that Eve's information is limited to what the theory predicts. They therefore overestimate the conditional minimum entropy. That inflated value is then fed directly into the privacy amplification step. Privacy amplification compresses the key according to this incorrect entropy estimate. Since the entropy was overestimated, the hash function compresses the key less than it should. The final key ends up longer than the security proof allows, and some of the underlying statistical structure remains. The result is a key that looks random to the eye, but is not fully secure in the information-theoretic sense. Eve retains more knowledge than the system believes, and the privacy amplification step fails to eliminate her advantage. When privacy amplification is carried out correctly, the final key takes on a very specific structure. It no longer resembles the biased and correlated raw key we saw earlier. Instead, it becomes a string of bits that behaves as if it were drawn uniformly at random. The key reason this transformation works is that the amount of compression is determined by the correct minimum entropy estimate. Once we subtract the information Eve could have gained from the quantum channel, the information she overheard during error correction, and the safety margin for statistical uncertainty, we are left with a guaranteed lower bound on her remaining knowledge. Privacy amplification compresses the key to a length that is consistent with this bound, and as a result, the remaining bits lose all meaningful structure. The output that you see here is a visual representation of the final privacy-amplified key. The individual values appear patternless, and there are no regions where the brightness or density suggests correlation. This is what information-theoretic security looks like. Even an adversary with unlimited computational power cannot distinguish this key from an ideal uniform random string, except with a probability bounded by the security parameter epsilon. This is the exact guarantee provided by the leftover hash lemma. Once privacy amplification is applied using an accurate entropy estimate, Eve's knowledge becomes mathematically negligible, and the final key becomes suitable for any cryptographic purpose. Here is a quick summary of the video. First, the raw key that comes out of quantum key distribution is not secure by itself. It contains statistical patterns and side information that an adversary may already have learned through the quantum channel or through the classical communication steps. Those patterns must be removed before the key can be used for any cryptographic purpose. Second, privacy amplification is the tool that performs this transformation. It takes a key that is only partially unpredictable and compresses it into one that behaves like uniform randomness. This step is essential for converting physical measurements into a secure digital key. Third, we have seen that an adversary can influence which detections survive. By subtly manipulating the measurement statistics, an adversary can create a raw detection record that is already biased in her favor. If the system does not correctly detect and account for that bias, the minimum entropy estimate becomes too optimistic. Fourth, accurate entropy estimation is critical. Even small mistakes in estimating the adversary's knowledge lead to incorrect compression and insecure final keys. Fifth, the leftover hash lemma provides the information-theoretic guarantee behind privacy amplification, but only when a universal hash family is used. Classical cryptographic hashes do not satisfy this requirement, and therefore do not provide the necessary security level. Sixth, error correction leakage and finite-size penalties must be subtracted explicitly. If these terms are ignored or underestimated, the entropy analysis becomes invalid, and the resulting key length is unsafe. Seventh, when privacy amplification is applied correctly, with the right entropy estimate and the right hash function, the compression step eliminates the adversary's knowledge, even when the adversary has unlimited computational power. Finally, the output of this process is a privacy-amplified key that is information-theoretically secure and suitable for any cryptographic use, including one-time pad encryption and long-term storage of sensitive information. Thank you for watching. If you enjoyed this video, please like and subscribe to the channel. It's free for you and helps us a lot. To take your understanding further, visit spectreai.ai, where you can work through 55 real-life quantum security labs and learn these concepts by doing. You can also explore our books on Amazon for complete coverage of quantum key distribution, quantum security, and practical cryptographic engineering. The books offer in-depth solutions to the online labs. Leave a comment below and tell us what you would like to learn next. Your feedback guides the direction of future videos. Thank you again for joining us. See you in the next video.